Okay, in this section, we are going to look at operational amplifiers. In the previous section, we just looked at how we can model electrical systems and get the transfer function out of it. And the reason we are looking at transfer functions is because we want to look at the relationships between the input and the output. Now, sometimes you will have circuits that contains operational amplifiers, and we want as well, again in this section, to be able to model the circuit using operational amplifier, and we want to look at the relationship between the output and the input as well, such that we will be able to write our transfer function of the system out. Because once we have the transfer function of a system, we will be able to design a controller when we do our control design. Now, what exactly is an operational amplifier? So in short, it's an integrated circuit like this chip here. It's an integrated circuit, and inside the chip you have a lot of transistors, resistors, capacitors, diodes coupled together in such a way that when you put a signal at the input terminal, you should be able to get a signal out. Either it will be scaled or it will be subtracted, etc., etc. Now, we are not going deeper to analyze exactly how this is done because this is beyond this course. But what we are going to look at is the basic of the operational amplifier and how we can model that when we look at different circuits. So now, there are different types of operational amplifiers, and the one we are going to look at is the 741. Now, pin 1, the offset null. The function of pin 1, this offset null, so in a nutshell, you can say that it's used to reduce the small DC offset that may be present at the output. Pin 2 is the inverting input, and it just means that if you have a signal, for example, this is at pin 2, and your input is that, all right? What you're going to get out, your output, it will be a signal that is amplified but is inverted. Now, pin 3 is the non-inverting input, meaning that if you have a signal that is there, that's your input, and your output is going to be an amplified signal, and it's in phase with the original signal, with the input signal. So this signal here is not inverted. Pin 4, that's your negative VCC. It means that that's your negative part of your power supply, because this amplifier need to be powered up. So you power it up between your pin 4 and pin 7. Pin 8, this is not connected. Pin 6, this is your output of your signal. So you have your two input, which is your pin 2 and pin 3, and your output will be pin 6. This schematic here represents a simplified version of this whole package, and normally when we are drawing this simplified version, we usually do not include the power supply. We assume that we know that there is a power supply. Otherwise, if there is no power supply, then we will be violating the conservation law of energy. There is no free lunch. Now, again, let me just redraw the symbols again for our operational amplifier. Here we have a schematic of the two amplifiers. They are exactly the same. We say that this is the normal drawing of it, and this is the reduced drawing of the amplifier. And we say that in this diagram we do not indicate the VCC, because we already assume that the VCC, the supply voltage, it's already there. And what we can indicate is we have the first leg is V1 and your second leg is V2. V1 is connected to the negative side and V2 is connected to the positive side. And note as well that V0, this output voltage, it will never exceed plus VCC and it will never be below the minus VCC. So in a nutshell, it's like saying, okay, if I have, let's assume that I have a signal whereby I'm able, maybe I have 20 volt here and I'm able to amplify probably this 20 volt into maybe 20,000 volt, and my supply voltage here, it's only 5 volt here and minus 5 volt there. I cannot produce 20,000 volt here. It's not going to happen. So if the maximum power supply here is 5 volt, then I'm going to be capped at 5 volt. And the dynamic of this thing, the way it works is, it has something called a saturation region, whereby you have an amplifier, this is the gain, and it gets cut there, and you amplify. By the time you reach around 5, you get cut off there. And this will be your 5 volt. And here you're going to have your minus 5 volt. So we can say that in a nutshell, so your V0 is between plus VCC and minus VCC. Now, before we start looking at how to model this circuit that contains operational amplifier, we need to make certain assumptions. And the assumptions that we are going to look at is assuming that we have an ideal op-amp. So if we assume that we have an ideal op-amp, then the first assumption we are going to look at is, let me just draw a circuit here so that we can work our assumption out as we go along. So assumption number one is, assumption number one says that no current, so we assume that there is no current that will ever flow into either input terminal. So that means that the current going in is 0. So the current that goes in here is 0. The current that goes in here, it's 0. Also, the current coming out is 0. The current coming out is 0. So no current is going in, no current is coming out. That's into the amplifier. So we might have to ask ourselves, how can this be? And the only way this can happen is, the assumption is that there is a resistor between the two terminals and the value of that resistor should be infinite. So if the value of that resistor is so big, the circuit will behave as if there is an open circuit. So meaning that you're gonna have a resistor between the terminal and the resistance for that resistor is infinite. So if you have very, very high resistance such that is so big, current will not be able to flow through that. Assumption number two. So assumption number two says that no voltage difference between the two terminals. So we can say that if we have an infinite resistance between the two terminals, that's your V minus and the V plus, then no current will be entering into the op-amp. This is like having an open circuit, as we said earlier, and this implies that the voltage V1 and V2 are the same. So if we look at this circuit here and we say, okay, there is no current that is flowing here, and hence there is no voltage drop, then we can say that the voltage at V1 is equal to the voltage at V2. So the two voltages, V1 and V2, are the same. Now, assuming that this amplifier has a high gain, and we know that the amplifier, they do have high gain, then V naught is equal to, this is your gain, times the difference between your V1, which is your V2, which is your V plus, minus your V1, which is your V minus. Now, since we said that V1 is equal to V2, we can say that the difference between your V plus and your V minus, let's say this is VI, whereby VI is your input voltage. Then we can say also that V naught is equal to the gain times your input voltage. Now, what we can see is most of the time amplifiers, because the reason for the amplifier is to be able to amplify a signal. It has a gain which we call A here. And this gain can be maybe 10 to the 4th, it can amplify it 10 to the 6th, it can amplify it 10 to the 7th, etc. So if let's say this gain A is equal to 10,000, and the difference between V1 and V2, it's so small. Let's say maybe it's 0.001. This will give us 10 volt. What if you make it even smaller? Again, 10,000 times 0.0001. This will give us still 1 volt. So looking at it, you have 0.0001. The difference between V1 and V2 is so small, but you are getting 1 volt out of it. So this is the power of amplification. So the next thing that we can ask ourselves is, how can we model a circuit that has an amplifier? There are certain ways an amplifier can be set up, and we're gonna look at this, whereby you have an amplifier with a supply voltage Vs, and we say that this leg here, that was our V1. So this leg here was our V2. Let's assume that we have current that goes here. This is I1, and current will go here is I3. Current will go here is I2. So from KCL, we can say that I1 is equal to I2 plus I3. But we know for an amplifier, the input impedance is very high. Here it is. We say that here our input impedance is infinite. If that is true, then I3 will not be able to go in there. It's going to be 0. So this implies that I3 is going to be 0 because of the high impedance. If I3 is equal to 0, then we have I1 is equal to I2. Now, let's find the current that is going through resistor R1. So we can say that I1 is equal to Vs, that's our supply voltage, minus V1 at that junction over R1. We have already said that V1 is equal to V2. So we say that V1 is equal to V2. V2 is connected to the ground. If V2 is connected to the ground, then V2 is equal to 0. This implies that V1 is equal to 0. So then we are going to have I1 is equal to Vs over R1. What about the current that is going through RF? We can say that I2 is equal to V1 minus V0 over RF. We know that V1 is equal to 0. So we can say it's 0 minus V0 over RF. Hence, I2 is equal to minus V0 over Rf. Now, we have our I1 and we have our I2, and we know the relationship between I1 is equal to I2. So we can rewrite these equations in terms of I1 and I2. So we can say that Vs over R1 is equal to minus V naught over Rf. So if I multiply on both sides with Rf, if I multiply with Rf on this side and I multiply with Rf on this side, that Rf is gonna go. And what I'm going to have is Vs Rf over R1 is equal to minus V naught. Or we can say that V naught is equal to minus Vs Rf over R1. So now when we did the analysis, we found now the equation of your output voltage. And we say that our output voltage is minus Vs Rf R1. But the output voltage is negative. It has been inverted. And we are going to look at that shortly. But before I do that, let me look at the transfer function, because that's what we are interested in. And the transfer function, we want the relationship between the input and the output. We can say that G of S is equal to V of S, this is now in the Laplace domain, over Vi of S. The Vi of S, that's still your input voltage, which is the same as your supply voltage. Okay, I just rewrote it. You could have written Vs here, which is equal to minus Rf over R1. So the output of this op-amp, let's assume that your input, our input, is just that sine wave. And we want maybe our output to be amplified. So the output is going to be a negative of that. So this will be our output, and this is our input. We can also write this circuit in terms of impedances, because if you have complicated circuit, you need to be able to break them down into impedance form. For example, if you have a circuit that has a combination of a capacitor, an inductor, or a resistor and a capacitor, a resistor, an inductor, etc., or 3 or 4 resistors, you should be able to couple them together and say this is impedance 1, this is impedance 2. Just reduce it to basic circuit. So we can have this circuit in terms of impedance, whereby we have Z1 and Z2. Our current, again, exactly the same as we've done before. You're going to have your I1 here, I2 here, I3 there. And we can write this equation by breaking it down just the way we've done it before, whereby we have I1 is equal to VI Z1, I2 is equal to minus V naught Z2. This implies that we have Vi of T over Z1 is equal to minus V naught of T Z2. This is now, I've written this in terms of time domain, so that we know from time domain to get the transfer function, we need the Laplace transform of it. Therefore, we can have V naught is equal to minus Vi of T Z2 Z1. You see, This is all in terms of impedance, and the impedance you are reducing circuits that contain capacitors, resistors, inductors, etc., into a simple form. So from here, we can write our transfer function, which will be V naught of S over Vi of S, which is equal to minus Z2 over Z1. So the transfer function is just a ratio between the two impedances, Z2 and Z1. Now, what if we want to, assuming that we have a power supply, this is a system, and the output here, our power supply, is 25 volt, and we want to drive a speaker or a microphone at 5 volt. 25 volt power supply, we want 5 volt. How do we do that? We know that we need to reduce that 25 volt to 5 volts so that we are able to power up this. This means we need to use amplifiers. We know that we are going to have an amplifier. Let's draw the amplifier here. So this is what we are going to have. Our input is 25 volt, and we want our output to be 5 volt. We want 5 volt here. We can see that we can have a ratio of a fifth, whereby we can say, okay, if we take R1 to be 1,000, and if we can take RF to be 200, this will give us this minus 5 volt. Because this is an inverting amplifier, we're going to have a minus 5 volt, as we've indicated here. Our output is always negative. But we don't want a negative output. What else should we do? Maybe we can add another amplifier. Let's see what will happen if we add another amplifier. So we add another amplifier. If we add another amplifier and we make R1 is equal to RF, all this does is just going to flip the sign. Because remember, from the beginning we had a positive input, positive sign input. What we get is a negative sign. Now we are inputting a negative sign in there, negative 5 volt. We're going to have positive 5 volt. And we can use this 5 volt to drive our mic. Things that we have access to, things that we have control over, is your R1 and your RF. The two resistors. We just play around with the two resistors and we should be able to get whatever we want from this amplifier. The next part is we want to look at non-inverting amplifier. Now, this part is non-inverting amplifier. And we can see that now the supply voltage is on the V plus side, or V2. Okay, we had your V1 and here you have your V2. And this is our supply voltage, Vs, okay, or V in. So again, our current is just like before. We have I1, we had I2 here, and in here we had I3. And from KCL, so from KCL, we know that I1 is equal to I2 plus I3. And also, we know that Vi is equal to V2, which is equal to V1. Since I3 is equal to 0, this implies that I1 is equal to I2. Hence, we can say I1 is 0 minus Vi over R1. And we know our I2 is equal to Vi minus V0 over Rf. If we simplify this, this is minus Vi over R1, which is equal to Vi minus V0 over Rf. If we cross multiply this, we're going to have minus Vi Rf is equal to Vi minus V0 R1. Let me just simplify this. Then we have VI RF is equal to VI R1 minus V naught R1. Take the V naught on the other side and take the VI on one side. We're going to have V naught R1 is equal to VI R1 plus VI RF. Factoring the VI out, we're going to have V naught R1 is equal to R1 plus RF times VI. Hence, V naught is equal to R1 plus RF times VI over R1. And this can be further simplified as V naught is equal to 1 plus RF over R1 times VI. So this is our V naught equation. We can see that V naught will never be below VI. It is always equal to VI or higher and positive. So if you are trying to reduce a voltage, it's not a good idea to use this circuit because it's either going to be equal or it's going to be increasing. For example, let's look at this. If RF is equal to 0, then RF is 0 over R1. Anything 0 divided by anything is 0. So you're going to have VI times 1, meaning that V naught is equal to VI. So this implies that V naught is equal to VI. Okay. Then the statement of V naught will never be below VI, it is always equal. So hence, for this, it is equal or higher. What if RF is equal to R1? If RF is equal to R1, then if RF is 10, R1 is 10, that's going to be 10 over 10 is 1. 1 plus 1 is 2. So this implies that V naught is equal to twice VI. That's still larger than V naught. What if RF is equal to maybe 15 RA? If RF is equal to 15 R1, this implies that you're going to have V naught is equal to 16 VI. What if you make it very, 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 very small? If RF is equal to maybe a tenth of R1, then V naught is going to be 1.1 I. So again, if you want to reduce your output voltage, do not use this circuit. What about the transfer function? Again, transfer function is very simple. V naught of S over VI of S is equal to 1 plus RF over R1.